Great. Well, it's very nice to have Elaine Lee here. She's from the physics department at University of Texas in Austin. And I've known her for many years. I don't know, 15 years, I'm guessing. I'm sure I met her at a FOPS meeting, a summer seminar, workshop for semiconductor physics. She did her undergraduate degree at Beijing University in the mid-1990s, 1997, I think. She moved to University of Michigan to do her PhD work with Duncan Steele, who that time in the early noughts was doing coherent control. And I think Elaine did one of the very first experiments in Duncan's group on coherent control that was quite popular. It was done in quantum dots, and it really set the stage, I think, for future experiments. She changed fields slightly and moved to JILA to work with Steve Cundiff, doing 2D Fourier spectroscopy from 2003 to 2006, and then she moved to UT Austin. I'd like to say that she has 2 children, and so she has, during this pandemic, like a lot of people with families, really stressed or been stressed by the work balance between homeschooling and taking care of her kids. And she'll talk today about Moire Superlattices in 2D van der Waals systems, quite popular topic these days. So Elaine, please go ahead.
Thank you very much, Glenn, for the introduction. Let me just say, Moire Superlattice is still a new type of quantum material. And at this point, we're mostly speculating the applications in quantum information science. Towards the end, I'd rather have a discussion, hear from the expert in the audience how they can best apply it for quantum information science. So let me start by thank the people who did all the hard work in the lab. And the people on the right are my graduate students, Ka, Junho, Jiamin, and they're the one who did all the hard work I'm going to present in this talk. And 2 theorist contributions, Fengcheng Wu and Lucas, are either students used to be in Alan's group or visitor in Alan McDonald's group, and they were instrumental helping us understand these materials. And we've been working with this material for about 4 to 5 years, and I've learned a whole lot from my collaborators at UT Austin and from all over the world. And this picture of my group really includes many undergraduates who either volunteer or spend many hours helping us preparing these materials. It's a rather tedious process, as you'll see. So I guess I'm going to take that I don't necessarily have an audience that work with all kinds of quantum material to begin with. So let me just introduce the basics of what do we consider quantum material. So normally for materials that are bulk, electrons are free to move in all 3 dimensions. And if we find a way to confine the motion of electron in 2 dimensions, we have made a quantum well. High-speed transistors are made of quantum well. And Glenn is an expert growing both quantum well and the system that we call quantum dot, where we actually confine the motion of electron in all 3 dimensions. In a way, we have produced an artificial solid-state atom. So there's, of course, in between, you can have quantum wire where the electron motions are limited in 1 dimension. So as you can see, by confining the electron motion into different dimensions, we change the possible energy states that they can occupy, and therefore modify their microscopic properties, such as light emitting colors, or statistics, how light is emitted. So if you were to put a single electron hole pair into a quantum dot, just like atom, once they're excited into an excited state, because Pauli blocking, they cannot reabsorb until that energy is released somehow. So in that case, you will get what's called a single photon emitter. So size matters. So if you take a rubber ball, make it just smaller, you get another rubber ball. So how small is small enough in quantum material? Really, the criterion is you have to make it small enough. You're pinching the electron wave function, so to speak. So this is a very popular set of quantum dots made in wet chemistry or colloidal quantum dots. These consist of one type of semiconductor surrounded by a core. When you tune the core size from 6 nanometer to 4 to 5 nanometer, you have tuned the emission color through the entire visible color range. So this is what we call quantum material, essentially engineer material property through quantum confinement. So many of us in the condensed matter or in material science area has been working on atomically thin material for the last few years or decade. For a large part, thanks to these two gentlemen, who figured out how you can create a atomically thin material by simply using a Scotch tape. So in their seminal paper published in 2005, they actually demonstrated you can exploit large variety of materials. Everybody have heard of graphene. That's a single layer of carbon atom, but they have also exploited what we call the transition metal dicogenide, which is a class of semiconductor. And with the band gap, they have a lot more, they have a property that make them suitable for light emissions or transistors or other type of application. They have also exploited material that turn out to be superconductor and sometimes complex oxide materials. And as we can see, when you thin these material to one or two layer, their property actually drastically change. So this is the power of manipulating quantum confinement, and these single layer or single unit cell material represent the ultimate limit in how thin you can make two-dimensional material. So I personally did not work on graphene because it doesn't have particular interesting light emitting properties. My own group mostly work on optical spectroscopy studies of semiconductors. So we do study metals as well, but graphene, it just wasn't in the right wavelengths of interest to our group. So we started paying attention to these van der Waals material when these material transition metal dicogenide, I'm going to refer them as TMD for the rest of the talk, start to emerge. So for a single unit cell thickness, there are 3 atomic layers. There is a transition metal in between, and then a chalcogen atom on both sides. If you look at this material from top down, you have a honeycomb lattice where the AB site are actually occupied by 2 different materials. So my own group mostly create these material by mechanical exfoliation. This is a rather small flake. With skilled undergraduate, they're creating flakes that are 100 micron in size. And also the growth using chemical vapor deposition has progressed significantly in the last 10 years. People can now grow wafer size, single atomic layer of these materials. And I should mention that this is not, at this point, no longer simply an academic interest. A semiconductor company like the company in Taiwan, which makes a lot of the chip that in the commercial product, they're actually starting to heavily investigate in this material, because in a transistor, when you try to shrink the size of a transistor, you need to shrink the thickness and the lateral dimension proportionally. And then in order to keep shrinking the channel length in a transistor, they also have to make the material thinner in the thickness direction. They believe these atomically thin material can play a role in future transistors. So they're investing in these materials, learning how to grow them over wafer size. So one of the paper that grabbed a lot of people's attention in this paper that appeared about 10 years ago now. And these researchers have shown that when you thin down the material and in a few layer thickness limit, the light emission is growing. And the particular dramatic change happened between 1 layer and 2 layer, where the light emission efficiency grow near 100-fold. I should say this particular material is studied as MOS2, and the monolayer form of this material has been isolated, back in the 80s and even published in a decent journal. So at the time, people were not interested in optical property. And so people like myself did not pay much attention to these materials. So what happens when you go from 2 layer to 1 layer? So you actually have a very drastic band structure changes. You change the indirect semiconductor to a direct semiconductor. As we know, light emission absorption process need to satisfy both energy and momentum conservation. In the indirect semiconductor, the top of what we call the valence band is misaligned with the bottom of the conduction band. So if you excite the material using what we call off resonance or some photon that's well above the band gap, there's a very rapid relaxation of the electron to the bottom of the conduction band and hole to the top of the valence band. And they have a mismatched momentum. For light emission to happen, it has to evolve a phonon to satisfy the momentum conservation. As a result, indirect semiconductors are not efficient light emitters. The most famous example, of course, is silicon. But when you, in these TMD materials, when you thin down to monolayer, it shifts the band structure such that the conduction and the valence band are now, the bottom of the conduction band, the top of the valence band are now aligned, and making the light emission process much more efficient. So these are early calculations showing you how the band structure changes in from the bulk form, 4-layer, 2-layer, and a single layer. And as you can see, there's only subtle changes from the bulk to the 2-layer limit, but from 2-layer to 1-layer, you can see the bottom of the conduction band shifted to what we call the K point. And so does the top of the valence band shifted from a gamma point to K point. And these K points are actually happening in the boundary, at the boundary of the Brillouin zone. So there are actually two inequivalent values that we're going to call them a K and a K prime value. And these colors indicate the spins of the electrons, or electrons are occupying these values. And the two transitions, the two low energy transition that's going to be responsible for light emission is that K and K prime value, which are related to each other by time reversal symmetry. And that is to say, if I have spin up in one value, I'll have spin down in the other value. And therefore, you can address these values using light, but with different circular polarization. So this is what people call value spin locking in these materials, and people are campaigning using value as additional degrees of freedom for information information processing. I should say that, of course, all semiconductor, all band structure have these values, and they're simply the minimal or maximal conduction band or valence band. Typically, these values don't respond to any external field and making them difficult to directly access. But these material has the property that turns out in the monolayer form, the lowest energy transition happen in these values that can directly be accessed through optical means. So if you were to use value as a degrees of freedom, any two-level system, we can represent them with block vectors, as all of you are quite familiar with. You can somehow ask yourself the question, can I manipulate carriers in these two-level systems for information processing purpose? So band structure alone is not enough to explain the light emission property. What happens is when you create electron hole pair, when you put the electron from the valence band to the conduction band, there's also a Coulomb attraction between the electron and the conduction band and the hole in the valence band. And then they form these excitons. What's different for this material is because the material is so thin, the Coulomb field between the electron hole actually permeate outside the layer, and therefore they're not sufficiently screened by the material. So dielectric screening is reduced. As a result, and also together with effective mass consideration, the binding energy for exciton in this material is very high. So they're on the order of a few hundred MeV. And of course, thermal energy is 25 MeV. As a result, these bond electron hole pair is very stable even at room temperature. And for the same reason, these unscreened Coulomb field make it such that trion, which is essentially a charged exciton, 2 electron bound with a hole, are also quite stable. And so is bi-exciton. 2 electron hole pairs can also bind together with a binding energy on the order of 20 to 30 MeV for these two species. So perhaps this is reasonably familiar with for the audience here. if you can isolate an individual electrons, individual excitons in all three dimensions, you can use them as single photon emitters. And they have very large dipole moments. The light emission for these material with a single layer material has about 10% absorption near the exciton resonance. If you take that, convert that to dipole moment, it translates to a huge dipole moment. So while it takes people a long time, Glenn knows that history very well to work with, to find the cavity QED effect with semiconductor quantum dots. These material, if you just put it even on a very lousy cavity, you can already easily get into the strong coupling regime and see polaritons and things like that. So that makes them very interesting from that perspective. And also because they're van der Waals bounding, you can literally put them on any substrate. So a lot of people are working on applications where you can make a photonic waveguide and you can just transfer the layers to where the photonic structures are. And you can harvest the light emissions quite efficiently and then build an interferometer, build a potentially integrated platform of photonics to do subsequent information collection and processing. So Trion is a great way to entangle spin and photon, and biexciton can be used as a source for entangled photon pairs. I have already mentioned this compared to the traditional 3-5 material. The large binding energy and large dipole make them easy to access at high temperature and manipulate to couple to cavities. So this is my few minutes of introduction for atomically thin material, actually 10-15 minutes. And let me pause for a minute and see if there's any questions from my audience.
So you just mentioned that the binding energy of these trions is larger, substantially larger. What is the magnitude? Right.
So the exciton compared to the free electron hole state is 200 to 400 MeV. And trion, if you count from how trion turned out to be energetically favorable, so they form at energy lower than exciton. The energy difference between trion and exciton is about 30 MeV.
I see. And what's the experimental signature of a trion versus an exciton?
So, so I don't have a perfect plot, but, you can, in this, if you just take these simple optical spectrons, either in photoluminescence or absorption, you see an additional peak at low temperature popping up at the low energy side of the exciton.
I see. So it looks as a satellite to the normal excitonic emission.
Correct. At a lower energy. And to confirm it's a trion, you can apply an electrical field or start adding additional charge into the semiconductor. Then you can see their weight goes up or go down.
This is Bill Phillips. I've got a question about the biexciton. You said that this was a good thing in order to produce entangled photon pairs. What variable is entangled when you and could you say a little bit more about how the entanglement works in that situation?
Right. So this biexciton can be mapped into a 4-level system, and where the ground state will be the crystal ground state, meaning no electron hole pair is excited. And then the next 2 levels are exciton states, where they're distinguished by polarization. So in this particular material, you can have 2 excitons in 2 valleys, both excited by opposite circular polarized light. And the biexciton is the 4th level. And then, this is, the entanglement there will be the polarization entanglement. I assume you can work on other degrees of freedom to get them to entangle as well. But, polarization is the easy one to identify.
Okay, thanks.
Other questions? Okay.
It looks like that's it for the moment.
Okay, thank you, Alicia. So, and now this is where everybody is going with this atomically thin material. So we want to play more games with just learn to get a single isolated layer. So one of the easy thing you can do is actually to take 2 materials and stack them vertically. And because the van der Waals binding, you don't have the strict requirement for crystal to be aligned, the axes to be aligned with each other. You can actually rotate the layers. As you rotate the layer, I hope you can make it out on your screen that once you increase the twist angle, there is a superstructure that appears, and the size of that superstructure reduces as you increase the twist angle. So this is what I'm going to spend the next 20 minutes convince you that now I actually have a whole array of quantum dots. Okay, so let me go beyond just a cartoon picture. And as I said, there's different ways to produce them. This particular work is a heterostructure produced by chemical vapor deposition. When things are grown on top of each other, energetically, they would align the crystal axes. So there's no rotation between the angle, but there's still a Moiré crystal because this two material combination, I taken the material combination where the chalcogenide atoms are actually different. One is sulfide, the other is selenide. As a result, the atomic lattice, the lattice constant, differ by 4%. So if they're not entirely the same, you can imagine I would have a gradual changes in atomic alignment. At one point, I would have what's called an AA alignment, basically the top hexagonal aligned perfectly with the bottom hexagonal. But when I move tens of a unit cell away, I can see one of the chalcogenide atom now stick out, the bottom layer stick out in the center of the top hexagonal. And then I have another situation that, it's reversed. I have three high symmetry points, at these three symmetry points, the atomic alignment is such that I still have the threefold rotational symmetry. So they're a little special in optical properties. And anywhere in between, I have these, not perfect alignment, either with the center or the atom. So I would naturally expect these gradual atomic alignment. And the picture I show you on the left are taken by by STM measurement, scanning tunneling microscopy. And this is topology, but this picture is basically a measurement of density state. So this is to say, I actually have this checkerboard where I have pockets where electrons tend to go to. Okay, so there's a higher density of electron densities there. So I'll show you more data to back up why that is the case. And of course, these not only naively you would expect these Moiré crystal to exist, they have been imaged with many different scanning probe technology or TEM. So this is a picture of TEM that you can just view where individual atoms are, matches the simulation. So the question is, how deeply are these electrons trapped at these sites, right? So I should mention this is obviously not an optical measurement because the dimension is very challenging for optical measurement. This is approximately 9 nanometer to 20 nanometer. So nobody has managed to address them individually optically, okay? But this picture represents how I imagine light emission will happen in this material as well. So let me show you another measurement, again, done by my colleague doing STM. So let's just focus on this bottom panel. So let me take a step back. So what my colleague did is to take a line cut in this Moiré supercell and ask the question, what is the local energy here versus, at the field selected point that have high symmetries. And so this is what they find. This is the energy gap at a field selected point within the Moiré superlattice. And you can see from one site to the next high symmetry point, the energy gap changes by 200 MeV. So that energy trap is deep enough to localize the electrons and holes and also electron hole pairs. So this is really what gives us confidence that we can consider them as an array of quantum dots.
Elaine?
Yeah.
Bill Phillips again. Now, it seems to me, now maybe this is a naive picture that I have, that with an ordinary quantum dot, the potential looks pretty much like a square well, because you have boundaries that are essentially atomic size, whereas with the Moiré pattern, you have boundaries that are rather soft, sort of sinusoidal.
Yeah.
Does that make any difference?
I think it does. So first of all, the potential in the vertical direction and the lateral direction is different. In the vertical direction, they're basically bounded by the substrate and the vacuum, right, the air. So that potential is pretty sharp. The wave function is, the thickness of these monolayers already on the order of 0.7 nanometer, and there's wave function extensions through this 0.7 or 1.4 nanometer. If you stack two layers, it's approximately, a little over one nanometer. In the lateral direction, it is softer. So, so it will change the specific energy level the electrons and electron hole can occupy. So this is what we know. So the next thing is we went ahead and measured their optical spectrum, right?
If I could just follow up on Bill's
please.
question. Is it right to think of the exciton here as sort of being more or less like a free particle with some dispersion relation in the direction that's parallel to the planes, and then a radiative transition is a change in the relative binding of the electron?
So I think that is mostly correct if you have a monolayer, but now you have the two layers, you also impose the lateral energy confinement.
I see. Thank you.
Right, so they don't move freely in the two-dimensional plane anymore.
I see, there's sort of channels or something like that.
Yeah, so now there's this checkerboard of energy modulation. And the field is right, it's not like a square well, because the atomic alignment is gradually changing. But that picture itself, this picture don't always hold for all materials. Yeah. You have cases that it look like a square well too. I'll get to that towards the end. If you can remind me to show you pictures, there are situations you literally have some quantum well due to lattice relaxation. That's the next level of complexity, what structure can be formed in these Moiré crystals. Okay. So now, okay, I think I might have swapped the, there's a, sorry, I think I missed the slide. It got misplaced, to a point. So, but this is important for me to talk about this in the right sequence. Okay, so now let's think about how they behave optically. What I showed you using STM is actually measurement of single particle bands and where the electrons are. So what happens optically, what I'm also making a sneaky change on you. I'm gonna show you two TMD materials now have the same chalcogen atom. This is MOSE2 and this is WSE2. So when I pick these layers with the same chalcogen atom, their lattice constants is almost identical. They differ by 0.1%. And now the Moiré size is really determined by the twist angle. So there's a reason why we chose this combination is because we want to see, can we make big Moiré cells, perhaps bigger Moiré supercells. First of all, it's a little easier to get to individually once we have the ability to use a near field measurement. And secondly, the size is completely determined by the twist angle. So when I excite them with light above the band gap, these semiconductors also form what we call the type 2 band alignment, meaning that the electron will tend to accumulate in one layer. There's where the minimum of the conduction band is. And the hole tend to go to the opposite layer. That's the, the top of the valence band. They're actually in two different materials. Okay, so as a result, I can have both these intralayer exciton where electron hole are in the same layer, or I can have this interlayer exciton where electron hole are in opposite layers. And these interlayer exciton, electron hole are in opposite layer, are more energetically favorable because of this band alignment. As you can see, if I take electron from one layer, hole from the other layer, I actually get to create this lower energy transition. Okay, So the correlation and where the excitons are in the Moiré cell are still under debate. But one can imagine, because this periodic change in the atomic alignment, there are 3 special points. So as I illustrated in one of the earlier slides, at these 3 special points, the rotational symmetry, 3-fold rotational symmetry is maintained. And if I just ask about, there's still 2 values, K and K prime, okay? But I'm not gonna follow only one value for now. If I just plot out the transition in one value, and the other value is just a time reversal copy of it. So if I follow the one value, and if I were able to put the electron hole at these 3 different sites, and they turn out they will follow different optical selection. So that is to say, forget about the value copy for now. Even I only follow transition in one value, I have both energy modulation in the Moiré crystal and optical selection rule modulation. So I have this checkerboard of emitters potentially, and they would follow a pattern of chirality as well. Okay. So, but remember these supercells are all on the order of tens of nanometers. So when I do a far field measurement, I'll be measuring 500 to 1,000 of them. There's no guarantee I can resolve these transitions or resolve their chirality at all. Okay, so this is a challenge for the optical scientists. So how do we tease out the feature that's associated with the Moiré? So we did that. We did just that, and it's important. Not only you need to stack 2 layers, you actually need to protect them with what we call, with HBN layer. HBN are high gap insulators. And that would just shield out some charge fluctuations. And when you make the high quality sample, you start to see some, here are the black dotted line are the bare Moiré crystals. And when you encapsulate them, this is the intralayer exciton, this is the interlayer exciton. When you encapsulate them, the broad peaks start to split into multiple peaks. But it's difficult to interpret these peaks. Because these layers, they do wrinkle, they have bubbles. It could be simply, I have some spatial inhomogeneity in strings that lead to these different resonances. So it's hard to make an assignment. So it really takes very diligent student making a dozen of these, and then we start to observe some trend. So these are 2 samples, and I'll just say these are our highest quality samples. Okay, so these are 1 twist angle sample, these are 2-degree twist angle sample, and we measure the spectrum at many places on the sample. And we see multiple transitions, as shown here. These are all the interlayer exciton, the lowest energy transition. And then there is a trend how the energy spacing change between these transitions. So the energy spacing between these peaks is on the order of 20 MeV. And remember, I've said that the entire Moiré potential is on the order of 200 MeV, right? So I can certainly fit in a few states in this Moiré potential. And the fact that, the 2-degree sample on average have higher energy spacing can be simply explained by I'm actually increasing the angle, making my lateral boxes smaller. When I make the lateral dimension smaller, I increase the energy spacing. It's like if you use the square well or harmonic well model, both will tell you the smaller lateral confinement lead to large energy spacing. So all of that is still difficult to nail down, but what's particularly interesting to us is in the 1-degree sample, you can see this transition have an alternating preferred polarization. So this is really a piece that's difficult to explain if you don't take into account the spatially existing varying Moiré potential. So this is one of our important hints that these multiple peaks are indeed due to the Moiré potential. So it turns out there's another way, another model to get you to the multiple transition with different polarizations. I've given you 1 example. If you have exciton localized at different point, they would have different selection rule. But there's an entirely different possibility. If the excitons find themselves in the global minimum, as Phil pointed out, these lateral potentials are actually kind of soft. They're gradually changing. So they're global minimums, and the energy trap is deep enough, I can have both ground state and excited state in the trap. And if I calculate the optical absorption rules for the absorption of these transitions, I also recover the alternating selection rules. And this is the center mass wave function for each of these states. So this is the model we adapted to explain the multiple peaks that observed in our measurement. Partially because we have other evidence, both temperature dependence and also energy dependence. But again, I'd like to pause and see if I have questions from my audience, because this is a lot to absorb.
Elaine, I'm wondering about how to understand what the optical radiation pattern looks like from this array of emitters that are spaced closer than a wavelength. So ordinary diffraction isn't really happening. That is most, except for the 0th order. If this were a diffraction grating, then nothing would exist other than the 0th order, because everything else would be evanescent. But now, are these things phased so that the emission is directional? And how should I think about what happens if I moved from, say, the near field to the far field? What this whole pattern looks like? It's just confusing to me.
Right. So nobody have done any measurement to address the question you just asked. Okay. And then should they be coupled to each other? I think the answer would depend on the period of the Moire Superlattice. So I can imagine when they get closer and closer, these things should be coupled to each other, right? And then whether they would emit coherently, like the classic, Dickey super state, we don't know. So they're actually really enticing platform to pursue these, because for Dickey states to exist, you also want to have a line dipole, right? And these dipoles are already aligned to some degree, because if you think about the interlayer excitons, they have electron hole separated in different layers. They already have a preferred orientation for the dipoles. So I think this is a great platform to ask the type of question you're curious about. So what is the emission pattern? Should they be coherently coupled? I think there's not a one size fits all. There's not a universal answer to that question. Okay. As I'll show you, many things are very tunable between by the Moire period.
But the excitation process itself does not create coherence between the emitters.
Right, not the way we're doing now. Most of the people excite them above the band gap, right? And there's a bunch of a relaxation process.
Yeah.
And okay. So there's no reason to believe these observations as of now is coherent, right? But you can imagine putting them to couple to a cavity, right? And then you can potentially coerce coherence or create them with a laser resonantly. Then you can imagine the coherence may exist.
Yeah. Okay.
Mm-hmm. Okay. So this is so let me just briefly show you. I don't have a whole lot of time left, but the energy, the fact that we assign them to excited state and ground state is also based on temperature dependence. The higher energy states are starting to disappear because they're escaping the trap earlier than the low, easier than the low energy states. So temperature dependence back up that there's also a systematic lifetime changes when we move across these energy states. So we've taken the interpretation of ground state and excited state. So I want to say this interpretation is still under debate in literature. So so there are certainly people who don't who chose to interpret them differently. So there's a whole main field group published almost simultaneously. People are focusing on very different spectroscopy features. Some focusing on these very sharp peaks that are found in these Moire crystals, and so these are just couple relevant work. But this is a very much new, and we're debating among ourselves what is the best spectroscopy signature to identify these localized excitons in the Moiré. So I should say there's a lot of details about how I made the argument I made. I had to make a number of assumptions. So one thing I should say, there's no simple correspondence between value and optical selection rule anymore. Even within a single value, you can have different transitions with different polarizations. And to provide that simple picture or simple interpretation I gave in the last 10, 15 minutes, I have to make a number of assumptions, and I want to be clear about that. So first of all, we assume that because the intralayer exciton absorbs more easily, we assume that their intralayer exciton created, and they convert to interlayer exciton, but follow the same. The relaxation are all happening within the same value. Only then we can have this alternating selection rule. Okay, and it's not easy to observe this alternating selection rule in all samples, because it's actually, anytime you're looking at luminescence, it's a result of a competition of several decay channels. So it's only when in the low twist angle cases you can hope to see this alternating selection. But nevertheless, based on what we understand, how deep the Moiré trap is and the energy spacing between these peaks, we still believe this multiple peaks likely arise from ground state and excited state. So here's a picture I want you to take home, kind of have this mental picture of what Moiré superlattice is. So first of all, I have to emphasize it's very tunable. So when you have small twist angle, when you put the Moiré supercells away from each other, our picture is you largely have localized electron holes for excitons. But when you make them smaller, make the Moiré superlattice smaller in period by simply increasing the twist angle, they become delocalized. So this is 1 degree, this is 3 degree. Of course, this is our cartoon, but it's this picture of localized and delocalized excitons are backed up by both our experiments and the calculation of property of this material. So I really want to get to the part I can discuss with you, the quantum information application. So I'll just be very brief and say, because the combination we chose have very similar lattice constant, you can actually grow them using chemical method, then you won't have any Moiré at all, because each lattice would distort themselves a little bit. You have a complete commensurate structure. So because it's so hard to isolate individual supercell, we feel we need this comparison experiment. Exactly the same monolayer, but without Moiré, and then with Moiré of different size. Okay? So what we've learned is that without Moiré, the exciton can diffuse over large distance, and with Moiré, with a small twist angle or large supercell size, they're localized as far as we can tell based on the optical diffraction limit. But when you make a 1 to 3 degree sample, they're different. 3 degree sample, you can start to see the diffusion. And finally, there's another subtle thing is the lifetime of this interlayer exciton are also rapidly changing with the twist angle. Because when I rotate the layer in real space, there's also rotation in the momentum space. That momentum space rotation made my transition to develop an indirect transition nature. And therefore their lifetime for the interlayer excitons is tunable from 1 nanosecond to hundreds or even longer, hundreds of nanoseconds or longer. So many properties are really truly controllable through the twist angle. So let me put out a few slides, last 3 slides, discuss how we can think about their applications. So one thing is really single photon, solid state single photon emitters. Currently, the single photon emitters are based on color centers, defect states in high gap material, self-assembled quantum dot, or modified carbon nanotube. A lot of people are finding defects in the layered material, but so far their performance is not nearly as impressive as other material platform. But all of these single photon emitters suffer from the downside of the locations are not defined, and there are size and shape fluctuations. If we can learn how to make this Moiré cell really well, then we would provide an entirely different material platform for an array of quantum emitters. So that's one direction, I think, and we know the energy trap is very deep. You know, in some other material, you can have 400 MeVs of energy trap for the Moiré cell too. But another very interesting direction is quantum simulation. So of course, the cold atom people have been doing quantum simulation for a long time, but Moire superlattice is in between the optical lattice and the real material because of the length scales, right? The length scale we have is 10 nanometer, and the energy scales is also very different. So you can take these Moire superlattice, and for the theorists are having a lot of fun. You can simulate quantum spin Hall insulator. You can simulate ferromagnetic state, antiferromagnetic states, or Hubbard model, and Elaine model. There's many things you can simulate. And I should say a lot of the early discovery of superconductivity or insulating states were made in graphene, but these TMD-based Moiré crystal is a better analogy for quantum simulation because the bands are simpler and it's easy to draw an analogy to these model Hamiltonians. And there are already early experimental evidence that support this picture of doing quantum simulation with these Moiré crystals. And again, very recently, there's a few papers appear almost simultaneously. And this is the paper coming from Jie Shen and King-Fai Max group, where they done both optical measurement and transport measurement. They show with a certain fitting factor, you know, for example, you put one hole into each Moiré cell, and you can start seeing an insulating state emerging. And then it turns out you also have some optical signatures as well. You know, the exciton transition also has some, the amplitude also are changing with the fitting factor of the carriers in the Moiré crystal. So I personally found both of these directions quite interesting, both pursuing single photon emitters and pursuing quantum simulations with these Moiré crystals. But certainly there's a lot to be learned and improved from a material point of view. So with that, I'd just like to thank you for your attention and be happy to take more questions. I can hear the silence here.
Sorry, it's a lackluster bit of clapping.
Yeah.
But so before we dive straight into questions, I realized I forgot to announce before the talk started that there will be a sort of discussion hour with Elaine after the seminar, and we will sort of amorphously transition from seminar questions into discussion hour. So people and students in particular should feel free to stick around and chat and ask more questions. And now I should open the floor for people that actually have questions.
So let me show one more slide to Phil.
Oh, sorry.
So, you know, actually the picture I showed you, like there's a continuous variation of atom, is a simplification. So in some cases you can have distortion because of strain. And then you have, instead of having these hexagonal lattice, you actually would have this triangular symmetry. And with this triangular symmetry, you have perfect alignment of the atom, and then they're separated by a wall that's a different alignment. So this is a situation where if you ask, can I have a square well? The answer is yes. In these lattice where they have their lattice relaxation, you have one area when atoms are perfectly aligned, then they relax their energy through a sharp boundary of a different atomic alignment. So this situation can be found in the Moiré crystal as well. So there's your square well model.
Okay, well, go ahead.
Okay. When you have a single layer, these van der Waals materials, the optical dipole moment gives you emission off the surface, I assume. Okay.
Yes.
But when you make this heterostructure, is it clear that the dominant dipole is actually out of plane, or is it actually in plane?
Right. So it's not clear. So first of all, let me say this. Even taking the simplest picture, you can have a dipole that have different orientation. And also when I say they're interlayer with electron hole in one layer and the other layer, it's a simplification. Remember, each layer is only 0.7 nanometer, depends on the detail of the atomic orbital hybridization. You can have electron, like for example, hole among two layer as well. So they're not vertical.
So it looks like there that the exciton orientation in those two excitons are orthogonal to each other. So is the emission also orthogonal?
Right. So this particular one is in plane. So people have done the measurement, and they seem to be mostly in plane. If you have a monolayer, you mostly have dipole in plane. So people have mapped, the K-space emission pattern and confirmed that. But very little has been done for the Moire crystals. There's more complications. Even if you take different material combination, you can imagine electron hole are actually distributed slightly differently between the two layers. So I think you still have defined dipole direction, make it still easier to coerce a coherent array of emitters. But it's not so simple like perpendicular, or in plane. It won't be such an
is there some experimental evidence that this heterostructure exciton is also quite bright, or is it slightly different?
They're pretty bright in the sense that in this particular case, the interlayer is brighter than the intralayer because they're energetically more favorable. There are other people claim they in the highest quality interface you don't have intralayer at all. Some of the papers that when you have heterostructure, the intralayer is only observable in absorption measurement, no longer observable in photoluminescence. So how bright are they? They're not as bright as epitaxial dots right now. So perhaps partially because we're not harvesting them as well, right? So they have this plane, and then the simplest thing we're all doing oftentimes. I don't think we're careful enough to think about how do I collect the light most efficiently. So there are more that can be done there. I think, I should say that there are people who already measure G2 of the Moire crystal, out of Moire crystal, but I don't believe those experiments prove they're single emitters because there's still far field measurement. And, it's odd to me, you can excite 500 of them and get G2 measurement. I think those measurements are actually selectively taking out the defect states that's present in the material.
Okay, great.
So
thanks.
there's some emission that are bright enough for people to do G2 anti-bunching kind of experiment.
So I'd like to return to my question about the difference between square wells and harmonic or sinusoidal wells. I can't see you anymore.
You mean that you can't see
this? There we are. Yeah. Okay. So here's the problem. When you were answering my question before, I lost you for I think the most important part of the answer, that you froze. And when you came back, Charles Clark was asking you a question. So what I want to know is whether the fact that in the square well, as I go to higher energies, I get bigger spacings, whereas in a sinusoidal well, as I go to higher energies, I get smaller spacings. Whether this has any important effect, or whether it's just the first two levels that you're worried about anyway.
Mm-hmm. Right. So, again, this depends on what material combination I choose and the specific twist angle. So in our measured cases for MOS2 and WSE2 for the near 1 degree sample, when we fit the energy spacing, they're roughly equal.
Uh-huh.
So therefore, we used a parabolic, we use this parabolic model.
Right.
But you can certainly find a situation, and we know they exist more in what's called the homobilayer. There's an important difference between the two. The homobilayers are created out of a single monolayer. That's why it's easy for the graphene people to do what's called the magic angle physics. They really need to stay within 0.1 or sometimes even 0.05 degree of twist, because then there's a subtle technical difference. They start with a monolayer, they break off part of the monolayer, they move over, and they rotate a stage. So this is a much more controlled process. We're doing that as well. So with those, you can create supercell that are a few hundred nanometer large. You can control the angle very precisely. So that perhaps is a better way if we're looking for quantum emitter array. That could be a better way to go forward. Our existing work were taken from two completely different monolayer. Then we don't have such a nice angle alignment. Then we're not in this regime of lattice reconstruction. So this lattice reconstruction is a square Waal regime, because within this dark and the gray region, there's no atomic alignment gradual shift. If you can think about the top and bottom layer, the atoms are gradually shifting, and then the energy structures are gradually changing. So you don't have a square Waal. But
Right.
here, you really have a situation. So here's a calculation. Here, you really have a situation that atoms are completely aligned within the triangle, and they're separated by sharp wall.
Right.
Of an entirely different alignment. There,
Because of the relaxation process.
yeah, lattice relaxation process.
Yeah.
And then you have this square Waal situation. We have not measured the optical spectrum of the square Waal situation here.
Okay. Lots to do.
Yeah, that's the puzzle, and also the material. When I was in graduate school, I have a colleague, we're all big fan of cold atom research. We read upon the cold atom research to figure out what we can do in solid state. My friends always said that God gave you atoms, right?
Well,
We have to stack them. Our students have to make these in the lab, and they're not perfect. So lots to
well, believe me, we do the same thing in cold atoms. We look at the condensed matter and wonder what we can do. So
that's good. So there's certainly a mutual respect.
yes.
Well, since you mentioned atoms, I'd like to ask again about the trion. So the way I think of it is you have an exciton, which is an electron-hole pair that's produced by, let's say, absorption of an infrared photon, binding energy of about an electron volt. And then the trion involves sort of the binding of an additional electron to that electron-hole pair. So it's sort of like the hydrogen anion or positronium minus.
Right.
And I'm wondering whether you can use the orientation of Moiré, the orientation of the sublattices as a sort of variable to tune the binding energy of the trion. And
Yeah,
get some
I
information
think,
about electrons.
no, I think that's absolutely possible, because this you bring up a really good point. This potential. Actually, if you think about the potential observed by the electron-hole pair, it's actually different from what the potential observed by a hole or electron. Another way to say it, the electron and the hole are seeing different energy modulation. So I think this is theorists like Alan Schuber actively working on. If you were to start doping this material, and the hole will find their own equilibrium state in this moire. And when you create the electron-hole pair, and it's not clear, the electron-hole pair will sit exactly where the hole likes to sit. Right, so I was just telling my theorist friends, it's like have the situation like the cold atom, you have a mixture of fermion and boson in this lattice. And follow what you said, if I were to have a stable trion state, it all depends on the detail where my electron hole pair, the boson, the exciton sit, versus where the hole sit, right? Again, I can have a variable situation, depends on the material I choose.
I think there's also, although it might not be so accessible, there should exist the antiparticle of the trion, where you have an electron bound to a hole and then another hole bound to that pair. And that should have the same binding energy with respect to the threshold. And I guess it's, you need to have two excitation events to get into that space. Maybe that's not so easy, but you could well imagine it only takes 2 electron volt, a visible photon, if you can excite 2 holes at once to probe that type of structure. Right.
So first of all, people have seen both positively charged and negative charged trion in these materials. And
have they? Could you email me a reference?
Okay, I'll look into that. So the effective mass for the electron and hole in these materials are very similar, making it such that the positive and negative trion have very similar energy. I can look into early literature in the monolayer, but that has not been sorted out in the Moiré crystals, right? Because the Moiré just brings so much more complications, and without the spatial resolution to look at them individually, and then still the peaks are somewhat broad. I think these are inhomogeneously broadened peaks, the Moiré excitons, and it's possible the trions are hiding somewhere there. So there's just a lot more to be clarified for spectroscopy on the Moiré. But I can certainly send you in the monolayer case, people have seen both the positive and negative trions.
So Elaine, this is Glenn. I'm curious in these trion states, these either pairs of electrons or pairs of holes are actually in different values. So the term must be, I would assume, weaker than the normal case where they would be in the same value.
Yeah, so you're again point out a possibility. Where are the electron hole, right? So they're in the material that's most heavily studied because it's particular band structure, WSE2. So people have seen trion, both intralayer trion and interlayer trion. What that means is intralayer trion, the electron hole pair and the excessive electron are in the same valley. And then interlayer, the excessive electron are in the opposite valley. And it turns out, if my memory serves me right, the interlayer exciton is yet again at a few MeV lower than the intralayer exciton.
Okay.
So make the intervalley trion, even in the monolayer, you can have both intravalley and intervalley trion, 2 species of trion. Depends on whether the excessive electrons sit in the same valley or opposite valley.
Okay.
So we have a lot of pseudo spin to play with here. So layer is a pseudo spin, valley is another pseudo spin. So sort them out is not always easy in spectroscopy. So you need the control sample with control the doping level. And of course, fortunately, there's a little bit energy difference between these 2 types of trions. Yeah, there's a lot. And then everything just get, triple times more difficult with the Moiré.
Hi, this is Teresa Ginley. I have a question. My background's in van der Waals epitaxy of bismuth selenide and topological insulators. So I'm kind of wondering if you had bulk bismuth selenide and then did a Moiré pattern with bismuth telluride on top, you no longer have the confinement of the substrate and the air on either side. Do you think that some of this Moiré pattern confinement would kind of seep into the bulk bismuth selenide and you could have a more 3-dimensional confinement?
Right. So how the dielectric layer changes the bindings is subtle. is more subtle than I made it sounded to be. So there, our collaborator have done these, how these transitions change with a dielectric constant as an environment systematically. They changed a different substrate. And it's not as simple as, the binding energy just changed and you see a huge shift in the resonance position. I think partially because, band gap and the binding energy all changes in a similar direction, in the same direction that made the absolute energy change different. So I would say, this is what, people like Tony Hines will call it Coulomb engineering. What he meant is because you can play with a substrate, you are changing the Coulomb environment, Coulomb field environment. But it's a little more subtle than changing it to 3-dimension. If you're not going to make the electron hole start moving in the other material, so it's not a true 2-dimension to 3-dimension transition, right? But you can ask how the dielectric constant would change the resonances or properties. It certainly also changes the lifetime, for example. As we know, the lifetime depends on the photonic environment. So it won't change the 2-dimensional nature, convert it to 3-dimension, because electron motions are still limited. There's a band gap differences, right? So they're still limited in the 2D plane. Did I answer your question, Teresa?
I think so. I think no one's really looked at just taking away the substrate and having like a bulk material. Yeah.
Yeah, that wouldn't happen from the electronic motion point of view.
Yeah.